This is me. I love the outdoors, but most importantly, I'm a born competitor. It doesn't matter who runs the fastest, finishes their exam first, or eats the most at Thanksgiving dinner. I show up to win. My desire for competition led me to graduate school in the field of chemistry research, and my love for the mountains led me to Utah State. This university has given me the tools I need to push my potential as a chemist, and as my story today has thrust me into the highest stakes competition of my life. This is also me. I'm an organic chemist. I take simple molecules and transform them into more complex ones, hopefully building a useful product in the process. My research is focused on renewable energy, and you may wonder, what's an organic chemist doing in this field? Don't they just need engineers to build turbines and stuff? Well, as I'll show you, deploying renewable energy on a massive scale is a problem left to the chemists to solve. We'll start by looking at Utah's energy production numbers. We get our electricity largely from burning coal and natural gas. These processes release harmful greenhouse gases into our environment, and we know this. There's no such thing as clean coal. And as a result, as a response, the category for renewable electricity like solar and wind is growing year by year. The US has steadily increased its deployment of wind and solar generation. This means we have more wind and solar panels installed today than we ever have before, and this is good for our environment. It means we can cut back on CO2 emissions from those coal and natural gas power plants. But now imagine a city powered only by renewable energy and completely separate from the grid. There would be no CO2 emissions to be found. But what will that city do when the sun goes down and the wind slows? Simply running out of power and going dark is not an option. We need an energy storage device capable of storing enough renewable electricity to safely power this city through the night. Now, this energy storage device must be reusable. And when you think of reusable energy storage, you probably think of batteries. You probably have a rechargeable battery in your pocket right now. Now, I want to scale up energy storage to power an entire city. And that means we will need huge batteries. And we can't just use AA's. Lead-acid batteries can't store enough energy and have too short a lifetime. Lithium-ion batteries have the performance we need, but at a sacrifice to safety. The larger you build a lithium-ion system, the more heat it generates, and this is a fire risk. I'm sure you've all heard the story of the Samsung Galaxy Note 7. You better not try to bring one of these on an airplane. And we certainly can't allow for this kind of hazard after the battery's been scaled up 1,000 times or more. So this is where my research comes into the story. I'm helping design a new type of battery to meet the need of our solar city, a flow battery. In this design, energy storage materials are pumped into the reactor cell through external tanks. Once inside, they can perform energy storage and then get pumped back out. This system allows for nearly limitless capacity by simply installing larger tanks. And by employing a fire suppressant saltwater solution, I can eliminate the fire hazard present in lithium-ion systems. This design allows me to safely scale up the battery without inadvertently building a bomb in the process. So this is what my battery cell looks like. The copper tabs at the top are the plus and minus terminals like you'd find on any other battery. And you can see that it's all bolted together because this is just a prototype. This design allows me to assemble and disassemble the cell easily to see what's going on inside. In this photo, you can more clearly see my battery with the energy storage materials dissolved in that solution sitting in those two external tanks. By pumping those materials into the solution, I can generate a chemical reaction and store electricity. But you're still wondering, what's an organic chemist doing building batteries all day? Well, I design the chemicals that go inside and actually do the energy storage. In these vials are chemicals that are soluble in salt water. Once in solution, I've engineered them to be able to store electricity. Now, some of these are easy to synthesize, and some are more complex. But I'm very proud of the fact that some of these compounds exist nowhere outside my lab, and that they can be used for such an important purpose. And I hate to entice you, but at least for now, the identities of these compounds have to stay secret. If you take a peek at my workbench, you can see it's a little bit busy, a little bit messy, and there's a lot going on, because this field of research is a race. I'm testing and synthesizing as fast as I can to design the right chemicals to build the best battery, because this design is well established, and other scientists recognize the advantages of this design. The only piece missing is what compound should go inside. So it's down to the organic chemists like me to finish the design. Researchers from Germany, China, Korea, and around the world are racing to develop these new compounds, and I'm racing against them. And the competition is only getting tougher, but with enough hard work and a little bit of luck, my research will make a difference for renewable energy. So with these batteries, as in life, it's what's inside that counts. And I'll leave you with a beautiful view of campus with the mountains behind. Next time you're cruising through the quad, take a peek in this window, and you just might see me at the workbench doing chemistry and representing USU in the competition to build the biggest, safest batteries. Thanks.